The title of the thesis is the Life Cycle Assessment of Emerging Batteries. My name is Cecilia Lander. I'm Associate Professor at Technology here at the department. And I have been appointed by the faculty to chair this session. So let me first walk you through the procedure. So first, Shan will start by presenting her thesis, and that will take around 30 minutes. Yes. Good. After that, the opponent will begin the questioning until that you feel you have thoroughly evaluated the thesis. After 1.5 hours, we have a break, and that can be in the middle of your opposition. So at around 2:30, when it fits. So we'll take about 15 minutes to stretch our legs and refresh ourselves. And then, of course, the opponent can continue for as long as needed. So once the opponent is satisfied, the evaluation committee will have their go. Today, the evaluation committee is online. And then finally, we'll open the floor for questions from the audience. After all the questions have been addressed, we'll conclude the session. The opponent and the evaluation committee will go to a post-seminar discussion where the evaluation committee will decide whether Shan will pass or fail. Okay, so let me introduce those involved. So we have firstly, of course, Shan, who holds a master's in environmental science from Wageningen, and has completed her postgraduate studies here at SLU at the Department of Energy and Technology. Then we have the opponent, Dr. Manuel Baumann, from the Institute of Technology Assessment and Systems Analysis in Karlsruhe in Germany. And then the committee online that we will see later. Or should I show them already, maybe? Let's see. There we go. So we have Professor Anders Nordelöf from Chalmers University of Technology. You can wave, oh, we can see your name actually. And the Swedish National Road and Transport Research Institute in Göteborg. We have Professor Christoph Halbig from the University of Bayreuth in Germany. And we have Professor Jennifer Dunn, that we're waiting for, from Northwestern University in Evanston, USA. We also have with us here in person the reserve member of the committee, Annika Nordin, who is an associate professor also from the department. And then we have Shan's supervisor group. We have the main supervisor, Associate Professor Åke Norberg, from the department. And we also have co-supervisors, Professor Per-Anders Hansson, there you are, and Hanna Karlsson-Potter, also from the department. Okay, so I think that's all. So before we begin, Shan, do you have anything you would like to add to your thesis?
Yes. Sorry, should I? There are two corrections that I would like to make about the thesis. One is in section 3.4, function 3.4, which calculates the energy stored over battery lifetime. And the equation was battery capacity multiply cycle life multiply state of charge and depth of discharge, and energy efficiency. The state of charge shouldn't be here. The second correction is in section 8, the future study. This is related to the study 4, all-solid state battery. It says lanthanum needed to produce all-solid batteries between 2030 and 2035 could be 166 times the current annual global production. It is a scary number here. But recently, I found a better data source for the current annual global production for lithium. the number after recalculate, it becomes 41% times.
Great.
Yeah.
Okay, so thank you. So I'll give the word to you now, Shan.
Thank you very much. So nice to see many of you here, also for people who is joining online. Welcome to my dissertation seminar with the title of Life Cycle Assessment of Emerging Batteries. So batteries are essential part of our modern society, directly and indirectly affecting our daily lives. It is used in different applications, from small-scale portable electronics, different electric vehicles, to large stationary energy storage system for grid applications. Battery market has been growing at an extraordinary rate. In 2023, the battery market in terms of battery capacity was 10 times of that in 2016. And if we look forward, the battery market is expected to grow at least another 4 to 5 times. Batteries are also expected to play an important role in decarbonization. This figure from International Energy Agency analysis shows that the projected CO2 emission from today until 2050 under two scenarios, today's policy landscape and net zero emission scenario. And there are a big gap between these two scenarios. Batteries can contribute to up to 60% of the CO2 emission reduction, with 20% of the CO2 emission reduction can be directly linked to the use of battery in electric vehicles and solar PV. And another 40% can be from the indirect use of batteries. For example, the battery facilitate end-use electrification and battery facilitate renewables. So the battery's importance in decarbonization and the growing demand for batteries encourage the development of new battery technologies to fulfill the needs in different sectors. For example, flexible organic batteries for flexible and bendable electronics, or solid-state batteries for longer driving range, higher energy density, and high safety vehicles. Sodium-ion batteries for cost-effective applications, for short driving range vehicles, and also stationary energy storage system. So these emerging batteries are studied in the PhD project. And it's important to consider their environmental impacts at the early development stage, so the battery design are still free to be modified to prevent the unwanted environmental consequences. Life cycle assessment is a commonly used tool to quantify the environmental performance of products. So far, there's no standard or guidelines for conducting LCA on emerging batteries. And there are two types of LCA are usually used. One is lab scale or pilot scale LCA. Another one is prospective LCA. And both of them are used in this PhD project. So the overall aim of the PhD project was to enhance the understanding of the environmental performance of three types of emerging batteries: an organic battery, sodium-ion batteries, or solid-state batteries, and also to explore approaches for conducting LCA on these batteries. So let's take a look on the overall structure of the PhD project. The x-axis represents time, present time T0, and future time TF, when the batteries are fully developed, are ready to be on the market. Y-axis represents the technology maturity, measured by technology readiness level, TRL, from 1 to 9, with 1 being the lowest, 9 representing the emerging batteries are ready to be commercialized. Study 1 was focusing on organic battery at present time T0 with technology readiness level of around 3 to 4 using laboratory LCA. Study 2 focused on the same battery technology but at future point in time TF using prospective LCA. Study 3 focused on 3 sodium-ion batteries at future point in time and forward using prospective LCA. When the study was conducted, the TRL of sodium-ion battery was around 8 to 9 already. Study 4 focused on 3 all-solid-state batteries at future point in time TF and forward using prospective LCA. And the TRL of these 2 all-solid-state batteries are 5 and 8. So we mentioned 2 types of LCA here. And in the later slides, we will take a closer look at what is the difference of these 2 LCA. So lab scale LCA's life cycle starting from raw material extraction, material processing, transportation, component production, battery manufacturing to the final battery product. Energy is used along the life cycle, sourced from a combination of fossil fuel and renewables. So the foreground system here are at lab scale, including battery manufacturing and part of the component production. Foreground system refers to the part of the system that stakeholders have direct control or influence, while background system refers to the remaining system over which stakeholders do not have direct control or not central to the study. Here, battery technology are also at lab scale. So study 1 was conducted based on systems like this. Prospective LCA is to study the emerging battery at future point in time when they are produced at industrial scale, which means the foreground system will be upscaled to industrial level scale, as well as the battery technology. As for the background system, if we assume for emerging batteries that was assumed to be on the market in the near term, then we could assume that the background system remain unchanged, which means that we can use the current background system data or the LCA database without any modification. And such system was used in study 2. So if we want to study the emerging battery at far future, then many processes in the background system will change and needs to be taken into consideration. For example, transportation will be more electrified, more recycled material will be used, energy efficiency and material efficiency along the life cycle would be improved in many processes. CO2 capture and storage technologies will be implemented in some processes, as also energy source will be cleaner. So study 3 and 4 was conducted based on systems like this, considering the changes in foreground system, background system, as well as battery technology. So in the following slides, we will take a look how these changes are considered in the PhD project. Foreground system upscaling, especially for the emerging chemicals that is still at laboratory scale. So we used empirical factors and processing equations to recalculate the materials and the energies required for each chemical reactions based on laboratory synthesis method. As for future battery technology, the data needed for conducting LCA is amount of materials for battery components, as well as the battery performance parameters such as specific energy. And such data is usually not available for emerging batteries. What is available is data related to material properties and electrode-related parameters. So we could use this as input in combination with assumed cell design, as well as some battery design equations to model or calculate the data that is required. For background system change, integrate for study 3 and 4, integrated assessment model remand was used to explore possible future changes in different sectors. Under two scenarios, SSP2 peak budget 500 and SSP2 NDC. And shortly, we will explain it in a bit more detail. A Python package premise was used to integrate the result of integrated assessment model to modify the corresponding production processes and emissions in LCA database, generating a set of prospective LCA databases under at different years under the selected scenario. Then later we can use this database for LCA calculation. So there are different scenarios used in study 3 and 4. Here, the background scenario lists two, as we saw just now. SSP2 refers to shared socio-economic pathway named middle of the road. It represents the continuation of historical trends in terms social, economic, and technology development. Peak budget 500 and national determinant contribution NDC are the climate target. If we follow these two scenarios, the surface temperature rise can be limited to 1.5 and 2.5 degrees respectively compared to their pre-industrial level by 2100. And in later slides, for simplicity, we will call them 1.5 and 2.5 scenario. Additionally, we also considered two scenarios for the future battery technology, a baseline and the optimal, resulting into 4 scenarios in total. So now let's dive into individual studies. And first, for organic battery, study 1 was laboratory scale LCA, and study 2 was prospective LCA with considering changes in foreground system and battery technology. This is how the battery looks like. It's still at laboratory development. It is developed by Nanotechnology and Functional Material Group at Uppsala University, who also provided the data, the laboratory data. And the battery consists 6 components. Anode and cathode are novel chemical called conducting redox polymers. And they are also developed right now at lab scale. And the structure is rather complex, but we can divide it into 2 parts. Backbone for electronic conductivity and pendant group for charge storage. And rest of the battery components are at commercial scale. Sulfuric acid was used as electrolyte. Separator is glass microfiber. Current collector is graphite. Battery casing is biopolymer. So the results shows that anode and cathode are main contributors in both laboratory LCA and prospective LCA, with cathode have higher environmental impact than anode. This can be attributed to the production of backbone structure, specifically the precursor 3,4-ethylene dioxyethylene. If we look at the relative contribution of different process flows in these 2 LCA, different bars represent different impact categories, and different colors represent different process flows. We don't need to understand everything. In general, we say that after upscaling, the relative contribution of different process flow changes. For example, the light blue here, which is solvent, it's the relative contribution of solvent decreased significantly. Comparing the total environmental impacts between these two LCA, after upscaling to industrial scale, the organic batteries environmental impacts reduced by 97 to 99%. And this is mainly due to the improvement in solvent use efficiency, associated reduction in waste, reuse of solvent, and catalyst. Comparing to its counterpart, flexible lithium-ion battery, as the green bar shows, the organic battery has higher environmental impact in most of the impact categories, except for ionizing radiation. This is mainly due to the low specific energy of the organic battery. Low specific energy means that more battery material is needed, or more battery is needed to provide the same amount of battery capacity, which associated to higher emission. So now, study 3, sodium-ion battery, which was conducted by prospective LCA, with considering the changes in foreground, background, and battery technology. 3 types of battery chemistry were considered in the study: layered oxide NMMT, polyanions NVPF, and Prussian blue analog NAPBA. All batteries were modeled in a cylindrical form with a diameter of 21 millimeters and a height of 70 millimeters. Within the battery cell is a winding battery layer, and each battery layer consists of different layers of battery component, including cathode, hard carbon anode, aluminum current collector, polyethylene polypropylene separator, and also liquid electrolyte, which is flowed in the battery cell. And battery casing is nickel-plated steel. So this is the climate impact result of 3 studied sodium-ion batteries and 2 lithium-ion batteries, which were included as benchmark. Between year 2025 and 2050, under 4 selected scenarios. We see that in general, all batteries' climate impacts decrease over time. This is due to the decarbonization mainly due to decarbonization of electricity grid. If we compare between battery cells, battery chemistries, we see that layered oxide NMMT has the best performance among sodium-ion batteries, which is comparable to lithium-ion batteries. This is because of its relatively high specific energy and also relatively low CO2 emission associated with the battery material. NVPF polyanion type has the highest environmental impacts, even though their specific energy is not specifically lower. This is because this is associated to the high emission of vanadium here. Vanadium was modeled as a byproduct of primary steel, which is a very high energy intensive process. So this shows the relative contribution of different material and energy flows indicated by different colors between studied year 2025 and 2050 under the 2.5 scenario. We see that this part, which is the cathode active material, are the main contributor, which is because of the higher amount of it used like a large amount of cathode active material in the battery cell. And for NVPF, it also associated to the use of vanadium, as we explained just now. Also, we see that over time, the relative climate impact contribution of this part, the battery manufacturing process, decrease. This is because this due to the more renewables used in electricity grid. So study 4, all solid state batteries used prospective LCA with considering changes in foreground, background, and battery technology. 2 types of all solid state batteries were considered in the PhD project. One is LFP as cathode and polyethylene oxide as solid electrolyte. Another one is NMC811 nickel manganese cobalt as cathode, and LLZO lithium lanthanum zirconium oxide as solid electrolyte. All batteries are designed as the pouch shape, and within the battery cell, the design is a stacking layer of unit layer. Each unit layer consists a layer of cathode, solid electrolyte, lithium anode, and current collector aluminum. Battery casing is aluminum polymer. So this shows the climate impact of 2 all-solid state batteries and 2 lithium-ion batteries, which was included as benchmark between year 2025 and 2050 under 4 selected scenario. And we see that in general, all-solid state battery has higher climate impact than its counterpart. This is mainly due to the use of solid electrolyte. And we also see the big difference between the scenario. This is a result from a battery design, different battery design scenario. So it indicates by optimizing battery design, the climate impact of all solid state battery could decrease by 46% for all solid state battery LFP, and by 35% for all solid state battery NMC811. Since the climate impact of all solid batteries are so sensitive to the battery design, we further included the best design scenario using the best possible design. So the result showed as the pink area showing here. It shows that after implementing the best battery design, the climate impacts shows of all solid state battery can be comparable to their lithium-ion battery counterpart. So when we look at the relative contribution of each material and energy flow between year 2050 and 2025 and 2050 under baseline battery scenario, it's very clear this part, which is the solid electrolyte, are the main contributor. And this is partially because of the large amount of material used in the battery cell, also because of the high emission associated with solid electrolyte material per unit. And for LFP, it's because of the use of lithium salt here. And for NMC811, it's because of the use of lanthanum oxide as precursor here. And if we count after also the anode active material and cathode active material have the significant contribution here. After optimizing the battery design, it also changed the relative contribution of material flow and energy flow also changed. So the relative contribution of electrolyte decreased and the relative contribution of cathode active material increased. So in summary, this PhD project studied 3 types of batteries, and the environmental hotspots are electrode backbone for flexible organic battery, cathode active materials for solid sodium-ion batteries, solid electrolyte for all solid-state batteries. Comparing to their counterparts, unfortunately, they all perform worse. But for one type of sodium-ion battery layered oxides, there is a potential for them to have comparable environmental impacts with lithium-ion batteries. And for all solid-state batteries, if we optimize their environmental impacts in the future, then there's also a potential to be comparable, to show a comparable climate impact with lithium-ion batteries. And besides, this PhD project provide a structured thinking for conducting prospective LSA on batteries with considering the changes in foreground, background, and battery technology. So future study. So this PhD project only looked into environmental impact, especially focused on climate impact. So in the future, other impact categories can be explored. Also other sustainable dimensions like the cost and social impact along the production chain and material supply risk. This PhD project only focused on the life cycle from cradle to gate, and in the future study use phase and end of life can also be considered. And besides, this PhD project only considered at battery cell level, and in the future study can integrate the battery cell into application like electric vehicles or stationary energy storage. Also assess their impact when they are large, the impact of large-scale production. These are some references used in the presentation. And in the end, I want to say thank you to my supervisors, also other people from the Department of Energy and Technology at Swedish University of Agricultural Sciences. Thank you.
Thank you, Shan. So now we will give the word to, I will give the word to the opponent that will first start with a presentation and give a bit of a context to the word. I will also give you this.
Okay, so thank you very much, Shan, for the great presentation. Really nicely prepared, and now it's my role to take a critical stance on your doctoral thesis. And here I have to take the role of the advocatus diaboli, the devil's advocate, which was not easy. So I will deep dive into your work and place here and there some questions, which we can then discuss afterwards on. So first of all, it was quite a journey for me to go through 157 pages full of knowledge. And I have to say I underestimated the effort. And there are 4 high-quality articles, 3 very different technologies that you looked at with, again, very different chemistries within those groups. You used multiple methods and combined them, which is, we'll deep dive into that, very good. And a lot of work was done. That is clearly visible. So I asked to myself, okay, how to put all these things together and to present them in 15 to 20 minutes. So I did the best here. So I think you opened this quite well. Why did you go into that field? Because there are some doubts on lithium-ion batteries. Yes, I will not go into detail. You addressed them. There are environmental aspects, things about supply risk, the performance of the same, etc., etc. So that is why these emerging batteries are an important thing with a gaining momentum, increasing momentum at the moment, in particular towards sodium-ion batteries. And as you have shown, you focused on the most relevant ones, sodium-ion batteries and the all solid-state batteries. The all-organic battery was not so in the core of my field, but still relevant, of course. And taking or trying to put your work into context, you really tackled a very complex thing: how to assess the environmental impacts of an emerging technology. And here, the TRLs are a proven concept, starting from 1 to 9. You showed that, until market system integration. And here you have the potential for sustainable design. You pointed that out, and the cost of adjustments, or the cost, environmental cost, whatever, increases over time. And here really the question is, how can we tackle this dilemma? So on the one hand, we have the information data availability, which you have seen. The higher the TRL, the more data is available. And unfortunately, on the other point, at the TRL1, you don't have a lot of data, which is a classical problem, in particular if you go to lab scale. And you have the power problem, how to steer the development of technology, and that was addressed quite well. So you looked at the laboratory scale and the industrial scale, and this is this goal of your thesis. I will not repeat it. And you applied here two stances, or two core versions of LCA, which is the pilot scale or lab scale LCA, the prospective LCA. You explained that quite well. I will not spend time on that. And also the works that are related to that, we gave a nice overview on that. So now, to put that in context, there is a very high demand for lab scale LCAs and prospective LCAs, in particular in the field of batteries, because there is a pressing demand from regulation. Yes, battery directive, for example, or looking at the critical raw material list and the Critical Raw Material Act on an EU level. There are plenty of examples that push the number of this kind of studies forward. So checking it in the Web of Science, you can see an increasing amount of studies being published, and they all have recommendations that are quite broad. So there's the search term, putting laboratory scale and prospective life cycle assessment into the search string. You can see that there are recommendations like optimizing cell manufacturing processes, the use of renewables for manufacturing, optimizing active materials, the electrode composition that has to be changed, enhancing battery life and efficiency, the recycling potential are typical things. Due to the pressure and demand, there is also a very extended discussion on these two methods. Yes, and there is an increasing amount of literature being published. And you address some of those, but later on I would like to discuss with you where you set yourself within this discussion. So the coverage of chemistries, sodium-ion batteries, there are plenty of studies already available. Yes, just mentioning some of them. Peter's pioneering it. And I'm not saying it because I co-authored it, but it is like that. And of course, there are other ones, very relevant studies, not all mentioned here. All solid-state batteries, there indeed it becomes very thin. And you tackled a very crucial point there, and will not talk too much about it. You showed the results, and they are verified also by the literature that I have shown there, which is also mostly mentioned in your thesis. And then I tried to look at organic batteries, and really is very thin, at least for closed systems. For open systems, so all organic redox flow batteries, there is more literature available. However, for closed systems, this is, I have to say, pioneering work. So I tried to think on how can I tackle actually or raise questions to your thesis. I mean, these are peer-reviewed articles, so looking into the results and doubt them, it would not would take too much time. We can't do that in the discussion. Maybe I will ask you some specific questions. But I was thinking, what are the challenges if you go into prospective LCA? That's data availability, laboratory versus industrial scale, scaling issues on the product, process, and use phase level, and temporal and systemic changes, which you addressed with the integrated assessment methods, and uncertainty. And if you put that all up, how do you handle uncertainty? That is a point I really would like to discuss with you. comparability of results regarding functional unit, the technology readiness level, or manufacturing readiness level. So all these aspects are addressed well in the thesis. And I also would like to know what is, in essence, the gap that you're tackling method-wise in your thesis, because there's a lot of literature, yes, and just to locate yourself there would be interesting. The data availability, laboratory versus industrial scale. Also here, there's plenty of literature available where they look into in particular, lithium-ion batteries and what the reasons are for the high energy demand in laboratory processes. So it's lower process efficiencies, the over-evaluation of technical building services, in particular the dry room. Then, of course, the production system is not optimized and you have a non-optimized product at the end, yes? So these are things that are addressed quite well here, and there's plenty of literature also focusing on the scale-up of different types of chemistries, just to name some, which is von Drachenfels or Eraksha et al. So what definitely is good that you did this pioneering work for the first closed organic battery, and that you really identified your hotspots. The question that I had also in reading sometimes the paper was, okay, I understood it now better in your presentation, but how did you gather the data from the lab? Was it just information of how the synthesis worked, or did they give you also information about the machinery, for example? Or did you do that all by scaling it up? We'll go into that afterwards. And also, how was the generated data? I mean, the scale-up methods, or the method, not all of them are scale-up or per se scale-up methods. How could you validate them, or what are your thoughts on that? On the product level, you developed two tools for modeling the cells that you assessed in paper 3 and 4. So there's a literature on performance mass models, and it's one of the most used tools to calculate the effects in the change of cells or new material compositions. And one line is there in your thesis where you point out a fair comparison of cells is of essence. That's, I would say, consensus in literature since some time, and there are plenty of performance mass models. I think the most known one is the backpack model from Aragon, the Celeste model from Wendka et al. And Greenwood based on Celeste, and then the one from Jens Peters and an older one from Berg et al., for example. And here, in your thesis, I would say it's always good to standardize that and to provide more models into that. But it would be interesting, what is different to the existing models? What does really make it better or easier to use? The next point regarding scaling is the process level. Yeah, so you did the upscaling on the product level, and here on the process level, you try to generate your unit processes, and you try to somehow to come from the lab scale and to see how it works on the industrial scale. You addressed that quite well in your presentation and also in the thesis. But how did you select your methods? Yes, was it just because of the data and time available for the assessment? And as you said, also in literature, most of the works that are doing this kind of assessments for LCA use process calculations. And there are plenty of different authors using different upscaling methods, and you used these, and of course others which are not mentioned here, but Piccino, which is fine, yeah, he's super often cited, and Geisler et al. For fine and special chemicals. So here, it's very good that you combine different methods, mostly referring, I have the feeling, to Piccino and Geisler, and that you applied this process engineering approaches, which are quite, I would say, a good choice. But in some cases, I did not understand why now this method, and how, for example, regarding the energy used for manufacturing, why did you take it from this source and combine it with that source? Yes, we can deep dive into that. And did you have the chance of somehow to validate that? Did you ask some process engineer, for example, if this could fit? Temporal aspects. I mean, this is a complex thing. Of course, you try to evaluate the potential environmental impacts of a technology, which you described very nice in your thesis, of a technology that has a low TRL and will enter into a higher TRL, let's say in 10 years, yes, and will be produced in the future. So here, the consideration of technological and socioeconomic projections is good. And here you used integrated assessment models, which are also gaining more and more momentum, which is good, yes. There are plenty of authors, and the most prominent one is the premise link to open to Brightway, and together with the Remind model. And here I see several benefits that you generated, or that is generated by the use of those kind of models. But there are also, I think, a lot of challenges, which is higher uncertainty, and higher uncertainty might also pose a problem if it comes to the acceptance of results to your peer group, maybe technology developers. The usefulness of applying such integrated assessment methods has to be really checked. So just because it can be done, it must not be done. So is it of interest for the stakeholder? So did you reflect on that? So the thesis explores very nicely the potential impact of sodium-ion batteries and all solid-state batteries, which is good, yes. Would say I'm not aware of other papers really focusing on those two types of batteries and using the scenarios. But the question is, I mean, the final conclusion that is derived is renewable energy sources should be used for the manufacturing process. So what is the added value of just doing some simple scenario? Using renewables instead of fossil-fueled power plants to show the impact on your product that you have at the end. So here, it's a kind of discussion. Where do you see the added value, or is it just enough to say, well, I'll do here 100% renewables for my manufacturing of the cells, or do I really have to play that until 2050, changing the complete sectors, putting carbon capture storage into play? I don't know, maybe in the steel industry to use direct reduction processes and not carbothermal processes, making it very complex at the end. So now coming to uncertainty, it's really difficult because you don't have any data which you can use to really validate everything. That's clear. And you need to do a lot of assumptions, yes? And those assumptions, I think you really did them in a really transparent way. But still, there is a high uncertainty inherent in prospective assessments, also in laboratory-based or laboratory scale LCAs. So this aspect of the complexity can make it challenging for decision makers to use the results because they don't understand how you calculated them in an extreme scenario. The parameter uncertainty that you have, so what do you assume how the battery works, what do you insert into your model, and the scenario uncertainty. I mean, you use established scenarios, yes, but still you build up the scenarios, so you have the parameter uncertainty and scenario uncertainty and the model uncertainty, which you do not have direct access, I would say, to Remind, for example. So you did sensitivity analysis and scenario analysis. You coped somehow the uncertainty, not somehow, you did it in a very well way, yes? And still, it's essentially to ensure the reliability and credibility. So your thesis did that in a very good way, I would say, and I'm the advocatus diaboli, I have to say that again. Yes, I have to raise questions. But looking at complexity and uncertainty, how do you see this issue? Because when you start, you have a lab scale LCI generation in paper 1, where you have uncertainties. You use that to upscale with different methods. Then you go into the product upscale with an own tool for building cells. And then you use integrated assessment models. And you combine that. And at the end, you might have a very high uncertainty. How do you communicate that? And at the end, you do not know the uncertainties related to the modeling. Taking an example of two different ways of looking at the same battery types. One time using Gabi and one time EcoInvent, coming to different results. So how to handle that, or what is your opinion on that? Comparability of results, you did that very nicely, I would say, but here I will not go into detail because I don't want to take too much time from the discussion. But in principle, you have the functional unit, which is very important, and and you pointed that out clearly in your thesis, very hard to define that. So one way to tackle that also could be the use of multiple functional units. The system boundary, also here you said you did not look at recycling at the use case, but taking other studies, you can see that the recycling, the upper graph from Peters, you know that publication, really shows that there's like a significant reduction in global warming potential if certain recycling routes are applied. Also, and you said we did not assess other impact categories in the use of the EIMs, integrated assessment models, because Remind focuses on global warming potential reduction, if I understood it correct. So that's why you did not look at abiotic resource depletion, for example, paper 3 and 4. But still, this would provide a very different picture to the sodium-ion batteries, just that you can briefly elaborate on that. So to conclude, your work is highly complex. You tackled a very dynamic field, and you combined, or you looked at a very broad set of electrochemistries, which is good, and even pioneered work here. And you used several methods, highly interdisciplinary work, I also would say, which is also very difficult. You did it in a very good way. You involved relevant stakeholders. You said that is future research, but you did it at the end in your work, I think. It was very insightful, and I learned a lot. And to conclude, the 3 final questions. It's very broad, the work, it's very nice, but what is the basic hypothesis that you want to prove in the thesis? And where do you see the biggest need for improvement in laboratory scale and prospective LCAs? And what are the most striking findings in your thesis that push the boundaries of the existing knowledge in the field? Yeah, that's it. I don't have any more slides. I have an anecdote. If you want, I can show an anecdote. An emerging battery. Am I allowed to do that? Okay. Because it is on emerging batteries, I thought I have to put this. Once a man said, just as soon as a man gets working on the secondary battery, it brings out his latent capacity for lying. Scientifically, storage is all right, but commercially and absolute as a failure one can imagine. That was Thomas Edison in February 1883. Just 25 years later, he said, inside of 15 years, the entire vehicle traction in large cities in the United States will be done electrically, and I'm now manufacturing the battery that will permit this to be brought out commercially with the Edison battery. Yes. Yeah, so that's battery industry announcements have to be taken with care. So.
Oh, the discussion.
Okay, so let's start. Do you want to address one of the questions that I made, or should I just repeat them and we go into discussion?
Yeah, we can start the discussion.
Okay.
Now. Yeah.
Okay, so in general, so the last 3 questions that I have put up, yes, because you did a lot. So I was wondering, reading your thesis, what is actually the hypothesis, the main thing you want to prove? Because in the research question that you have, you say the aim is of understanding, or I have to look of understanding how a prospective and lab scale LCA can be carried out and to identify hotspots. And
that was one of the aim, and
yeah.
also to explore the environmental performance of the three type of battery, like all organic and all solid state and sodium ion batteries.
Yes.
Yeah.
But in the way how you did it, yes. So was it rather putting together or saying, well, I want to look at this use cases, but was there also a methodological interest? So why starting from lab scale? Why going to integrated assessment models?
Yeah, because there was not so many, there was no study have done like to put the batteries in the future. So so the PhD, so we were wondering like, okay, if we put the battery in the future and then compared it with the current lithium-ion battery, and what could be the changes like in the comparison, yeah.
Okay. That is, I think, the third goal, that you wanted to compare it to existing technologies. Yes, I think in the specific goals you mentioned that. But what is the insight that you get from that comparison? I mean, you showed technology A performs worse than the lithium-ion battery, but what is the information that is valuable for the technology developer then?
Because different for a specific technology developers, because we have scenarios related to the battery technologies. So it's rather specific. It's like related to the battery design, especially for if we look to the fourth study, it was related to like how thin each layer was addressed, because that was also like the uncertainty. I mean, when it comes to like future batteries, nobody really knows like how battery will be designed. So yeah, we included different design and see how the design shifts the environmental impacts, climate impacts. And it shows that, okay, if the thickness of the solid electrolyte could be lower to this level, then actually the climate impact of a specific sodium or solid state battery is comparable to lithium-ion battery. So that is, I think, like a quite key message for battery researchers, also like for engineering, like to the stakeholders who's working on upscaling all the process, like to aim for how to process such thin layer and how to put each layers together, and also ensure like the same battery performance in terms of like cycling life and everything. So I think that's the key message, just to let them know, okay, we need to aim for such thin layer or such design. And if we could achieve that, then there's a potential that a solid state battery could be comparable.
Okay.
To lithium-ion. Yeah.
I understand that. And the goal of the single papers and use cases is clear. But in the way how you put it together, what was the overall hypothesis that led you to do that, what you did? Yes. So was there a driving thing that you say, well, I expect this or that kind of result. That's why I have put together this use cases, or was it just technology driven? That you said, oh, this is interesting, I'll pick that up because there's some missing literature.
Oh, you mean the overall for the thesis, like
yes.
different? Yeah, actually, we started from like the organic battery, which is like for super specific niche application, and also like the TRL was like really low. And it was like more like a rather learning process. So the first study, we say that we only did laboratory scale LSA. And during the process, when I was reading more, I learned prospective LSA, and I learned, okay, we could change the background system and to say, to say like a more longer term future climate impact.
Okay.
Yeah, that's so the at the super beginning, there was the aim of the thesis was not really settled. It was more rather like a learning process.
Okay.
Yeah, from study 1 to 4.
Okay, so it was evolving, you say. So you started with the lab scale with a research question on environmental impacts, and then it evolved. So there was not, let's say, an initial hypothesis.
No.
Okay.
Yeah.
You mentioned the TRLs, the technology readiness levels. Yes, there is other literature. Greenwood et al., for example, they have something called battery technology readiness levels. or there are the manufacturing readiness levels. So why exactly did you go for TRLs? Because I saw in paper one you even mentioned the MRLs, the manufacturing readiness levels, and at the end you go with the TRLs. Could you elaborate on that? Thought behind that?
Yeah, I think there are different ways, different type of TRL definition even. We were trying to pick like the most commonly used one, and the one that we are using is used by European Commission. Yeah.
Yeah, but
Yeah.
reflecting, for example, on the manufacturing readiness level, and as you do the process upscale, did you look into the literature how others do it to reflect also on the TRLs? For example, I think Wickert's use the MRL in her paper on the lithium sulfur battery.
You mean upscaling method or
No.
TRL definition?
Yeah, the TRL MRL discussion, because here you point out the TRLs of all the technologies just to reflect on that, because looking at it, you say the sodium ion battery has, for some components, which I think is very good, by the way, that you structure it after components and not the technology has a TRL of 9. But for example, asking the sodium ion battery is settled here to 9. So if I would take an NMC battery, where would I put it with the TRL? Also 9.
Yes, because TRL and MRL is different. Because the highest level of TRL represents the battery technology or emerging technology is ready on the market or ready to be mass produced. But after that, there's also a process of like market penetration, and it takes longer time for them. Yeah, there's a like then the MRL comes afterwards.
Yes.
Yeah.
But for separating the technologies analyzed, you have an NMC 811 and an LFP lithium battery. They would also be, for example, the electrolyte material and other components. Okay, the other components are fine, and the cathode material, anode material, TRL 9. So reading that, I would think, well, the sodium ion battery is as far developed as the lithium ion battery.
Yeah, that's TRL probably is not. It's not really good for differentiating like the real difference between sodium ion battery and lithium ion battery. But I think I mentioned TRL of sodium ion battery is like between 8 to 9.
Yes,
Yeah.
you mentioned it. I'm just also asking out of curiosity, because we were or are discussing a lot on the TRL classification. And if you would ask, I would say technology developer 1, you would say, well, it's difficult, maybe 7. Then you ask the next one, and then you said, well, it could be 8, yes. And then you read CATL announcement, Gigafactory, TRL 9. So did you have a discussion with technology developers on the settlement of the TRLs?
It's more like I read the definition from the European Commission for sodium ion battery, and then I decide I feel like it fits around 8 to 9, and for all solid state battery, that's the judgment from the battery expert from
okay. Yeah, because it looks quite promising, the all solid state battery. This is something like the holy grail, I would say, for lithium ion batteries, if you're able to have a solid electrolyte. And reading it, would suppose, oh wow, we're almost done. Yes, is that the case?
No, technology wise, I mean, there are sodium ion batteries on the market, but it's still like there are a lot of like technology issues related to it. So to really theoretically, of course, all solid state battery can achieve very high specific energy and higher safety, but it depends on like how thin, yeah, now it comes to the detail, like how thin the solid electrolyte could be reduced. And right now, that's always like the difficult in reality. I mean, there are some all solid state batteries on the market, but the solid electrolyte is not pure solid. It's more like half solid and half liquid. Yeah.
Yeah, there's a discussion on what is an all solid state battery, what can you classify, how, and you also mentioned the review from Prasad Mandade, which essentially also validates what you found out. Also to stress that you did a nice job with the thin electrolyte and to display the effects on the global warming potential. Yeah, so you showed that quite well.
Yeah, also like solid electrolyte, how to put them into application when it comes to like electric vehicles. There's a lot of vibration when we actually drive it, and some solid electrolyte actually is quite crispy. It's very easy to break, and there are different issues that related to the actual use. Yeah.
And that's a good starting point. You said the use phase, yes? In your works, maybe I did get it wrong, but for the sodium-ion battery and the all-solid-state batteries, you made some assumptions on the cycle lifetime, yes? And if I did not read it wrong, you also looked at that in the LCA then? So you considered the different lifetimes leading to the better results from, for example, the Prussian blue analog variation that you have. And could you briefly explain how you did do that?
How did I select the lifetime?
No,
or
how you modeled it in detail. So for the sodium-ion batteries, because I think you wrote the pessimistic cycle lifetime was 7,000, or I can't recall the number, 7,000 cycles, and the optimistic one, 15,000 cycles. How did you model the use phase then in your LCA?
The use phase was not really included. It's more like we considered the cycle life in the functional unit.
Yes.
But when it comes to the use phase, we didn't consider the use phase, the actual use phase.
How did you include the cycles into the functional? I know the functional unit is the kilowatt hour delivered.
Yes.
So how did you do that?
It's just divide like the cycle life.
Okay, so you took the cycle life, the amount of energy that is throughputed in the battery, and divided it.
Yeah.
So you have the total. Yeah, you showed the equation total. Okay, I see. But considering the use phase, what kind of environmental impact could be caused by the battery? Because in that way you miss one part, the efficiency.
Yeah, it depends on like the use phase, right? Because if we use it in the electric vehicles, then the energy is just gone. But if we use it as like under stationary energy storage, then it's just like store energy and then it will give back. But of course, there will be like energy loss during the use phase, and that part is not considered.
Okay, and if you would consider it, how would you do it?
Because there's like energy efficiency.
Yeah.
Then just to use to calculate, okay, how much energy is lost during the I would consider like how much energy is lost during the use phase.
Yeah.
And that will be yeah.
Okay, I'm glad we did it that way. So okay. And considering that you said, okay, we have put that into the functional unit, I understand that now, but what does that say about comparability of the systems? Taking, let's say, maybe a very extreme example. You use lead acid batteries for uninterruptible power supply. You have one cycle a year. The battery has 300 cycles of lifetime, optimized for uninterruptible power supply. and you compare it with a lithium iron phosphate battery, which has a cycle lifetime of 6,000, 10,000 cycles. So how to compare that? The lead acid battery fulfills perfectly the job. But in the way you consider the functional unit, it would, like, at the end say, increasing the cycle lifetime is good, should have to be done always. Yes, but it's not like in a context of a specific application. So how do you see that?
Sorry, could you repeat the lead acid part
Yes,
again? Yeah.
It's just an example.
Yeah.
Yeah, the application case is very important.
Yes.
So and how did you reflect in your thesis on it? How critical do you see that? So if I use a battery for uninterruptible power supply, where you have one cycle a year for testing it, and an extreme event, I don't know, 1 in 10 years, where you really need it. And if you look at, I don't know, providing some ancillary services for frequency regulation with a battery, you would have completely different results. But in the way how you modeled it, I think you just put that all like over one same.
I think it's quite hard to. I think functional unit shouldn't carry all this comparison, because it's limited in a way. Like so for this kind of thing that cannot be considered in the functional unit, we could use multi-criteria analysis, like also to consider other dimensions, which is very important for the application, but which is hard to consider it in the functional unit or discuss it in the way. Because I mean, for choosing the different batteries for application, the first criteria should be like the battery should do the job. And then we consider like their environmental performance.
Yeah. Though that is, you explained it well. And I would have to look it up, but is that also so critically reflected in the papers?
I think for regarding like the limitation of functional unit, probably paper 1 or paper 2, we shortly discussed, because it was also for us very hard to find like the counterparts to compare, because it's a very unique application. It provides like a flexible and bendable, which even though we compared it with flexible lithium-ion battery, but the flexible lithium-ion battery is not as flexible as the organic battery. So that part, I think that's something also like other study was discussing for emerging batteries, or if it provides like new features, how to best compare it. I think functional unit probably it's cannot really reflect all the functions.
Yeah, that's very true. That's a big problem.
I was thinking like if we could use multi-criteria analysis and just to identify like different stakeholders, let them to weight like the importance of the flexibility, the importance of the environment, and also like how flexible it is, also give it like a weight. Then in general we can still compare it, but not as a LSA form. Yeah. Okay.
And out of curiosity, in the study that we did, or actually in all the studies we do on emerging batteries, we struggle a lot in finding this type of data: efficiency and cycle lifetime. And for example, in the paper of 2021, okay, that's already 3 years old, but it was super difficult to find numbers on sodium-ion batteries, and those numbers were mainly like based on some lab-based tests on some cells. And then you had some startups like Tiamat showing, well, we have the cell 5,000 cycles. But at the end, also with discussion with our technology developers, they were quite skeptical with the numbers that we provided. So did you discuss also these numbers with others? And how was the selection?
Yeah.
I quoted, by the way, our paper.
Yes.
Which is,
because it was hard to find. I indeed it's I agree very much. Come to use phase is always difficult to find data because laboratory data really cannot reflect the reality. For sodium-ion batteries, like the cycle life was considered, and thanks to your study, for all solid-state battery, actually we didn't include the cycle life. That was because we had a discussion with the battery developers, the researchers. They are all actually not sure about the cycle life, and I mean a lot of literature mentioned that okay, because of the different mechanisms of all solid-state batteries, theoretically, all solid-state battery could have longer cycle life than lithium-ion battery. But for them, it's just like it's very hard to bring it to reality. I mean, theoretical is theoretical. That's why we actually didn't consider that part.
okay. Yeah.
Sorry, I was also I wanted to reflect to the cycle life that's used in sodium-ion batteries. I had a discussion with expert in industry afterwards, and for them, they were like, actually, the number that we are using, actually, I think we use similar numbers, is too optimistic. Under current condition. And that was also one of the reasons we decided, okay, we exclude cycle life for all solid state battery, even though it provides like limited scope but it's like just reduce the uncertainty, because play with a cycle life, it really changed the final results a lot.
Yes, that's very true, and you can see it nicely also in the results that you showed. I mean, you show the bandwidth. That's good. Yes, so you adequately address that issue. But we are mainly talking about cycle lifetime. But there is another aging effect, which is the calendric lifetime. So how a battery gets less and less capacity over time, depending on the surrounding environment. So taking, for example, again, the use case. I'm sorry. After that, I will proceed. 15,000 cycles. Let's imagine the battery has a calendric lifetime of 15 years. So what dominates? What is more relevant? And what does that with the functional unit? You understand what I mean?
Yeah. Yeah, there are two type of cycle life that can be considered in the functional unit. I think it depends on the application that we are talking about. For stationary energy storage, probably cylindrical, cylinder lifetime is more relevant than vehicle electric vehicle application.
It depends. I think there are studies that look at that. What could be a sufficient number for so looking at equivalent full cycles of batteries like NMC for automotive applications, and it's not so high. So that's why they're optimized also towards a certain cycle lifetime. That's at least what I have what I have learned. But taking a stationary application where a Prussian blue battery might be applied 15,000 cycles. So one cycle a day over a year, 365 cycles. So over 10 years, it would be 3,650 cycles. 20 years, the double. So it would be a very long calendric lifetime, get the 15,000 full. But at the end, I understand why you selected the functional unit, but it is a critical aspect, I think, to also consider this other.
Yeah, that's true.
Type.
Like, because in reality, probably the cycle life is much longer than the calendar lifetime.
Yeah.
Yeah.
They
also like battery technology evolve over time, and after they might
Yeah.
I mean, people who use like them as at home for stationary energy storage probably also change probably after 8 years or something, far before like the theoretical cycle lifetime.
Yes.
Yeah.
Yeah. Okay. So you're aware of that? That's very good. Okay. Coming to the lab scale LCA. So what was the most difficult part for you? What did you get from Uppsala, and how did the process start? So, and maybe to make it more a question, what would have been the best case that you get from them to do your work?
Yeah, the best case would be I will answer in another way. Like the data that we got is just like for example, the amount of reagent and the amount of solvent that is used in each of the chemical steps. And then we used the synthesis. But I mean, at lab scale, people don't really care about how efficient the material and energy is used, because which is like very relevant at industrial scale because it's directly related to the economic perspective. But at lab scale, it's more like what people folks or interested in is to test if it works. If such reaction works, if they could get like the wanted chemicals by such reaction. Okay. So like the material use and energy use was very, very inefficient. So that's why we need to recalculate it for each of the step. Okay. Yeah. It's By the way, you did a nice job with the synthesis in the organic battery. I think very thoroughly assessed. And you used Geisler, I think is his name, for the fine special chemicals, and Pacino. And I was wondering, for Pacino, you have to know certain things like the size of a reactor, for example. Yeah. So did you assume that by yourself, or did you speak with the Uppsala team on how it looks like? Actually, we discussed that, but they had no idea because it was I mean, it was wrong stakeholders. Okay. Yeah, because for battery developers, as I mentioned just now, they have different focus. Yeah. So they were more focusing on the laboratory scale, how to do the work. But for it was like a very special application, very niche for like wearable devices. And also conducting redox polymer is like a fine chemical, which means that it will not be really like a large production scale. So we actually selected like the smaller because there are different reactors. Yes, I know. Like you can select from a table where it goes up until 10,000. Yeah, so we actually we were quite conservative in terms of this. We were choosing like the small reactors, which means like the energy efficiency and everything is like more cost more per unit. Okay. And did you have any difficulties in, for example, looking at the specific heat capacity of solvents, for example? Because the specific capacity, yeah, because there are some with the equations from Pacino in particular. Yes, because it's sometimes for specific reactions, it's like a combination of solvent rather than like one solvent. Yeah. So if it's our assumption is that if there's like one dominant solvent, then we use the specific energy of that one dominant solvent. Okay. Specific energy, heat capacity.
Yeah,
Yeah.
specific heat capacity. Yeah.
If there are several, then we do like we just combined them together.
Okay. Okay, I understand. And regarding the comparison of the organic battery and the upscale, you used one source from Hio et al., which is from 2010.
Which one? Sorry?
Wait, I have to check it because
Yeah.
it's quite a lot of material, so I had to make some notes. But there is one source in the scale up, the battery that you use for comparison, which is rather old. I think it's like from 2000. So was there no other source available, or what was the reason? I'm trying to.
Oh, there was
find it.
one from 2004, and there was one Picino, I think, is 2016.
No, not regarding the LCI, the reference system we used for the organic battery.
Is it for like the nano
Yes,
for
this
flexible lithium-ion battery?
Yes,
Yes. Yeah, I looked into like different sources,
yeah,
and that source was like has the most like inventory that
okay,
is needed.
yeah,
Yeah, that it was like a quite old source. I think that was like a high uncertainty related to that.
yes, yeah. I don't find it that well. I marked everything, but
Yeah, it's in the paper too.
yes.
Yeah.
No, it is Majima at all. Also regarding the lifetime assumption, 4,000 charging cycles, but it was excluded in the functional unit as far as I understood.
It's in thesis because with time passed by, I realized that's the high uncertainty of the cycle life.
Yeah.
That's why in the thesis, we use the same functional unit to calculate everything, excluding like all the cycle life and everything. And the cycle life was specifically discussed in the section after that.
Yeah.
So it's just like to have like more certain results, and then also discuss a bit how the cycle life could change the results. Yeah, that's how the thesis were organized. But in the paper, we did include the cycle life.
Okay.
Yeah, and because of the specific chemical that was for the flexible lithium-ion battery, and the cycle life is quite long.
Yeah.
Yeah.
Yeah, that's true.
But it was like also very high uncertainty because the cycle life of that was not really for flexible lithium-ion battery, it was for normal lithium-ion battery.
Yeah.
And flexible lithium-ion battery is different design, and in reality, like it would be like folded because it's like for wearables. So all this practical thing, I think, will also affect the cycle life.
Yeah.
So that part, I think, really need to rethink if later study wants to, reading, that study.
Oh, okay. Yeah, let me see. You mentioned uncertainty. Maybe let's go to that. You applied integrated assessment models. And when you recall in the presentation, I asked for the reason, because why not making a simple scenario? What would change the final statement? Using more renewables would be good or better, instead of really taking a complex model and doing that until 2050. What is the added value of using, and it's a provocative, I would say, provocative question. What is the added value of using an integrated assessment method model?
It's easier to consider all the changes along the life cycle. It's not only like for the foreground system, that's the part of the system that we could control. Also like the background, all the energy related and everything sources will be changed, and material efficiency. And also before using, it's just like before you implement the integrated assessment model, nobody knows how the results would look like. So, I mean, of course, eventually we get the same conclusion, but before conducting such study, we don't know if we would reach the same conclusion or not.
But yeah, at the end, you could just easily change the background system by, I don't know, just changing the process from where the electricity comes by adopting it to 2030 and some projections. So not doing it so dynamically, there are pros and cons. I was just wondering, in the discussion with somebody who's developing, let's say, some all solid state battery, yes, to explain, look, the impact looks like this and that because the entire system changes. And I'm not fully aware in the integrated assessment models if, for example, I think you mentioned one paper that the steel industry is being decarbonized in the scenarios.
Yeah.
Aluminium not, for example. So that remains the same. But then you have a bias in the comparison, because it's relevant for the vanadium based sodium ion battery. So because you use it as a co-product, by the way, I like that with the different allocation methods that you apply.
I use the same method as I think one of your papers.
Yes, but that's not why, because you have put it there and discussed it also with the ERMs. But there, I just recognized, okay, it seems that the steel sector is being decarbonized in the scenarios. Is it like that?
It's like the production efficiency. Will be it's considered.
Okay.
Yeah.
To be increased, but not for other sectors, like for aluminium production.
Yeah, there are different. Actually, it's there are a lot of uncertainties regarding using of integrated assessment model. Because some sectors are considered in a more detailed way, and some sectors like chemical industries, then it's not really considered. So because it's remanded, it's also it focuses more on the energy system. So I think it's
but by that, so if you say it's uncertain, to understand what is happening, isn't it better to make like this ceteris paribus, to say, well, I'll do everything under the same conditions and I'll just change certain parameters that I have under control in order to understand better what my final recommendation is. So if we go to a technology developer, instead of that is the peer group, I mean, that depends on the scope and goal definition. But if you use an integrated assessment method for the assessment of a product like a battery, if it might not be an overshot, yes. So did you see, if you talk to a cell developer and you present that results, so do they understand that? Do they accept this kind of results, or is it too complex for them? Did you have the opportunity to talk about the results with guys from battery development?
Yeah, actually, they are more interested for battery part, because there are two types of scenario that that's the paper considered. One is about the background, which is considered by using integrated assessment model, and another part is related to the battery technology and the battery design, different design. So for them, they are more.
Sorry for interrupting. You combined both.
Yes.
So you used for the technology scenario also the integrated assessment model. So the two different models. You did not separate it. So you did the technology scenario and the backgroround scenarios, which makes it difficult, I think, to understand what contributes to what. In some, yes, it's one scenario. I understand that, but it's very difficult to explain that to somebody who's not in the field of LCA.
Yeah, I think it's like more like as LCA practitioner ourselves, we need to. It's rather complex because many things will change when we plug in so many different scenario and models. I think for us, it's very crucial for us to understand what is the core thing that we want to deliver, that we want to communicate with the stakeholders.
So
not presenting all the stuff with them.
yeah.
Yeah.
So in tendency, would you say in the goal and scope definition, who would be the right person to address in applying integrated assessment methods? Is it really the guy in the developing the cell, or rather, I don't know, system integrator or policymaker?
I think it's more for policymaker or for like a bigger picture, or more general, because it's related to different sectors. So I think it provides quite good information, like if it matters when a certain sector gets decarbonized and to what extent it matters.
Yeah. Yeah, and I mean it's in progress, right? It's being refined the integrated assessment models that are there. And
Yeah, as you said, I think plugging the integrated assessment model, like that part, probably is not so relevant for battery researchers. The battery technology like performance model part is more relevant to them because they have the direct control for that part.
Yes.
How to design and everything. And for the integrated assessment model, I think it's more for general different industries.
Okay. Okay. Yeah. I agree with that. Complexity. There's a discussion ongoing with the integrated assessment methods to have dynamic characterization. Okay, you're laughing. What is your opinion on that? Time. Okay. Okay. Yeah, I did. Very good. So the last question was your thoughts on dynamization of characterization factors for integrated assessment models.
For me, I didn't use it because I used the IPCC like for 100 years. I think it also because it's like the year is like long enough to be considered. So I couldn't tell. I'm aware of that. There's like a certain different studies going on, like for integrating the dynamic characterization greenhouse gas emissions. But I didn't use it. Yeah, because then I need to read, because I feel like every time when you add more elements in the model, then for sure you need to understand it. So then one could explain the results really to pick like what is which affect which is like the main effectors.
Talking about characterization factors, in the first two papers you use ILCD, which is now how old? 13 years? 2011?
Yes.
So why did you use ILCD and not the environmental footprint? The recommended method on a EU level.
I wasn't so sure. I think at that moment there was no environmental footprint.
Yes, but you could in the thesis have addressed it. Yes.
Yeah. That's true. I didn't address that in the thesis.
Yeah.
But since ILCD was like the recommended impact category, LCIA method for each of the impact categories. So that's why we choose it for the paper.
Yeah. Okay, I see. All right. So
yeah, that could be addressed in the thesis, but no, unfortunately, we didn't consider that. It was a bit old, indeed. Yep.
Yeah, but okay. We already have plenty of time. I have a lot of questions, as you see here. I'm just thinking what I really should address. and whatnot. What I was curious of in the paper number 3, I think it was paper number 3, where you use the values for manufacturing the energy demand. You use yuan et al. 2017.
Yeah.
Why?
Actually, we conducted the study. I aware that recent years there are like a lot of like good informations gets published,
Yeah.
like a detailed energy consumption regarding the manufacturing processes. But by the time while we were doing the calculation, it was not really it was like the most detailed inventory that we could find, even though it was the inventory for producing one type of lithium-ion battery.
Yeah.
So that's why we included, we used that for the sodium-ion battery calculation.
Yeah.
Yeah, but eventually the manufacturing process didn't really contribute that much.
Yeah.
Yeah.
Okay, yeah, okay, and this because of the electricity use that is there in at the end, then because of that.
Yeah.
Okay, but Yuan et al. I mean, you're upscaling to industrial scale, and there is from yeah, there are 2 publications focusing on that. That's why I'm asking on studies.
Different skills.
Yes.
Yeah.
Yes.
Yeah, I read that.
Yes,
Yeah.
and Yuan et al. I think it's unclear if it is pilot or industrial scale. So
yeah, it was not really a big scale.
Yeah. So that's why I'm asking, and also.
Yes.
Because there is, for example, this publication from Moody Cordia, I think from 2022. Is it 2022? Where they upscaled the pilot scale manufacturing plant modeled by Ellingson to the Northvolt reference. That's why you also, I think you even cited Cordia because you took the values for the battery casing from him. That it's just a detailed question on why specifically using that, because there are others also. But it's at the end the difference is not very high, and as you said, the impacts at the end are not that critical.
Yeah, I think that was because the inventory that they provided in the Yuan literature was very detailed, and we wanted to relate the energy consumption with each of the steps, like the electrolyte mixing and coding or something. And a lot of inventory that is available, even though it's more updated, but they don't exclude like all the details. So it's very hard to see like, yeah, to differentiate each steps.
Okay.
Yeah, that was the main reason.
Okay.
Yeah, because I think it's also tricky, like how do we actually use the results? Because the results of manufacturing energy could be aggregated in different ways. And a lot of paper, when they cite or when they use like the results from other papers, probably just take like a simple value, like the amount of energy per kilowatt hour of battery storage, or the amount of energy per kilogram of battery. And when I think I remember I did a simple calculation, the value actually shift quite a lot. And that's why I was thinking it's more reasonable to relate the energy to the amount of cathode and anode used in the battery cell, because that's like each of the step.
Yeah.
Even though it's like a bit older reference here, but I think the uncertainty is still lower.
Yeah.
Yeah, when we relate to each step.
Yeah. That is a good point. That surprisingly, people take that very uncritical, these overall values, like from, I think it's Deng et al., like with this one publication on the energy use, with this one publication from Argonne Laboratories, which has then been cited in, I think, literally every LCA on batteries. Okay, so what else to discuss? Yeah, out of curiosity, you write, and I think it was correct back then when you wrote the paper, that sodium-ion batteries are something that can, or that they are competitive to lithium-ion batteries in terms of cost. Is this still the case?
I think it's a very interesting question. It really depends on like the cost of lithium.
Yeah.
And I mean, but I think in 2022 the lithium price shifted quite a lot, like increased suddenly, and then last year or then it decreased a lot. Also, like the battery cell price. I think longer term, if it's not for investment advice or anything. For longer term, I think based on the amount of demand of battery, the lithium price will not decrease anymore. And the reason why lithium price decreased recently is because while it was increased before, a lot of Chinese companies, they bought too much. And right now they produce too much of the cell, and also they have a lot of stock.
Yeah.
As well. But it's all related to the reason behind of it. But if we look at like a longer time scale, I think it's still like the price, it's competitive of sodium because it's everywhere. It's not only about the price, it's also like the source is lithium source is quite concentrated to South American area, and in terms of the production, it's like the also around 50% is produced in Australia right now. So it's also like a supply risk. Yeah, different things I think to think about.
Okay, so you think it's a temporal thing?
I believe it's a temporal thing.
Okay, yeah, because I thought, what is it at the moment for lithium iron phosphate of 50, $60 per kilowatt hour, which is quite destructive for any other battery industry on the world. Okay, so yeah. Regarding the allocation, you have because we have been talking about economic factors now, for the allocation of the
vanadium.
Yes, you have gone for the economic allocation, and then the physical. So what is more reliable, because vanadium pentoxide is also in terms of cost something like going this, depending on the amount of steel being produced in China?
Yes. I think it's quite hard to say what is reliable, but I think what is good is like when there are like multiple products, if their economic value has like very large difference, I think it's good to use economic value to allocate, to reflect like the like the parts who is have higher value also carries more environmental impacts. It is also quite aligned with the general how it is dealt in general LCA database in EcoInvent. And also like in practice, when using economic value, it's always good to use the average of the previous at least 5 or 10 years. So just to cut some uncertainty.
Yeah, I agree.
That's my
because, well, allocation, what comes up into my mind then is recycling. In one paper, I think for in the paper you did not do it, but in the thesis you recalculated that you have some secondary materials coming into the manufacturing process of sodium-ion batteries. How did you model that? So did you, no, just explain how did you model that? What were the assumptions?
There are different, like the recycling, it was like more like the recycling content. I considered lithium, cobalt, aluminum, copper, manganese. Yeah, like it's just to it was in a form of like, for example, for lithium, it was in a form of lithium carbonate.
Okay.
So it's like in the form of chemical.
Yeah.
If it's the recycling content, it was not recycling rate, it was recycling content, like how the percentage of the secondary material used as the input material.
I understand. But then you did not consider the burden of recycling processes?
No.
Okay.
Because I also think, because it was like we look at like different years.
Yeah.
And when the battery is produced, it's like in a short term production. And at that moment, when you consider recycling, then the benefit is considered.
Yeah.
But then after that is the use phase. Use phase is several years after that. And then the end of life is several years later. So it's also like there is a time perspective.
Yeah.
Since we're only focusing on like the battery production process at that time. So we didn't.
But in that way, okay, now it depends. If you do not consider these burdens and the energy used for recycling, you might benefit chemistries that use abundant materials.
That's true. Benefit lithium-ion batteries.
Yeah.
Yeah.
Yeah, you favor the lithium-ion batteries.
Yes.
Yeah, yeah.
Yes. It's so I think it's very important when communicate such message.
Yeah. Yeah. No, I said it the wrong way because in the study with Peters, we saw that deep recycling does eventually not make sense in terms of global warming potential. You have to put more energy into recycling of sodium-ion batteries like Russian blue, because what you get out at the end is not that valuable. So primary sourcing might be.
Yeah, one of the reason that sodium-ion battery that study the recycling process was not included, even though there was already a paper like the paper that you published included such process. We also consider the more practical, like in reality, like if it could be recycled because it's cheap and if it's economically feasible to recycle, because there's already a lot of discussion related to how to best recycle lithium iron phosphate, because a lot of study was like, unless there's like a big subsidy goes to this market, then the industry itself will not recycle it. It's very clear because it will not make any benefit.
Yes, very true. Yeah, that is verified by past publications from our group. Very good. Okay. So maybe going to more general picture, because we're already quite some time here. People are drinking coffee. You mentioned that there is need for future research. So in the thesis, you point out like the social aspects should be somehow considered. Do you have any idea how? What should be done?
Yeah, it's also a bit tricky. I feel like when it comes to social, along the production chain of the battery, specific data is required, but it's as far as I know, it's a big data gap in this field. And when we look at how it is done now, there are several indicators that can be used, like what has been done in the critical assessment, mineral criticality assessment, like the governance index or HHI to indicate how concentrate of the materials. Such indicator could be used, but it's very general in the term.
Yeah. And considering, let's say, an equivalent approach to LCA, like social life cycle assessment, do you have any thoughts on that?
I think it's also like related to how easy to get data because, for example, if we want to measure like the working condition of the labor, child labor, and everything, then one really needs to have the time and funding to really go to the sites and to collect the data and all the surveys. Yeah, I think it's quite challenging for considering the social part.
Yeah, that is very true. I can confirm that. Database is very.
But what I know is that usually it's very interesting. Industry, they have much better data, but they actually have such data, but usually it's not shared in public.
Yeah.
Especially for the battery manufacturing, for some battery manufacturing, they actually conduct such research. Unless, yeah.
Yeah, but it's part of the battery passport. I think you have to. Isn't there a child labor factor? I think so. Okay. Last question. So talking about the different impact categories that you have, abiotic resource depletion, global warming potential, eutrophication potential, everything that is there. And let's think maybe also social impacts. You have supply risk. So how to handle all these factors. So what is your recommendation? Trade-offs, how to look at that? What could we do to get like a recommendation at the end?
Recommendation for
if this is a sustainable battery or not.
Yeah, I think it depends on who do we communicate. Because now how I'm thinking right now, when it comes to supply risk, it depends on like which country. Because one probably it's risky for it's more critical for one country but not critical for other countries. And also it depends on who do we communicate. Different stakeholders has different priority.
Because you mentioned before MCDA, multi-criteria decision making,
yeah,
and to involve different stakeholders. So, but it goes in that direction.
Yeah, because I'm just thinking that because the recommendation it really depends on recommendation for what. How do we use the results? Then depending on the different the goal, then the weighting will be different for different dimensions.
Yes. Yeah. Yeah, true. I like the response of it depends. And I agree with that. It depends really on the stakeholder that you have there. I think I have asked enough questions and I'll leave the space. Thank you very much for the nice discussion.
For
leave the space now for others.
Thank you. Okay, so we're going to move on to the evaluation committee. You can go and sit there.
Oh, okay.
And you can. So we have to. So now we just have to get the. There we are. Now we can see you. So who wants to start in the evaluation committee?
Doesn't
Should
matter.
I just say, we can say we start with Anders because you're up in the corner here, and then we go by where you are on the screen. Yes.
Okay, thank you. I would like to start, Shan, and say thank you for a nice presentation and a good discussion and a well-written thesis. I have a few questions to complement the discussion. I think that you, Dr. Baumann, did a really good job on some of the things that I wondered about, but I have a few things which I want to also go a bit deeper on with a few questions then. So there is, in the fourth paper, you talk about, or you write about what you call an optimal design. And I would like you to just discuss that a bit more, because I wonder in what way is that optimal in relation to the possible applications? And can you really optimize a battery cell unless you know what it's going to be used for?
In general, when we talk about all solid state battery, it is used in electric vehicles.
Yes. But in the paper you write about, you are modifying the cell design, but you are not providing a full investigation of how that cell operates in a pack in a vehicle. And of course, the performance and the characteristics of the cell, to me, that the full understanding of that would be in conjunction with modeling how the application works. So in what sense is it optimal?
When we talk about optimal, it's more like comes to the thickness of each component layer, anode, cathode, and solid electrolyte. Indeed, we didn't really consider the application part. It's more like focusing on the battery cell level.
Yes, but in order to make a battery cell for an application, you have to work with the different porosity parameters, the different thicknesses, and so on. So you work with for example, you want to have a specific power capability, you want to have energy capability, and so on. So the cell is typically designed for a specific purpose. So when you leave that purpose out, what are you optimizing for? What does it mean when you have an optimal layer thickness if you don't specify how the battery will be used?
I think that is a very good point. I think in general, the results could provide the battery researcher that which parameter is more sensitive to like the climate impact. Like because for here it's like comes to the solid electrolyte, just by make it a bit thinner, then the climate impact is like would be much more increased. So it's more like providing like a general trend for them in general. Okay, if they want to also consider the environmental perspective, then which part of the cell that they could work on.
Okay. Yeah. So yeah, you answered my question. It's optimized based on the greenhouse gas emission profile.
Yes, only considered greenhouse gas emissions.
Yes. So this means that if somebody could use that cell, that would be the minimized greenhouse gas emission cell to put for a specific application. So if you can find the application, then you have the perfect cell. Is that a proper way to interpret it then?
Yes, but then we also need to consider the battery performance, right?
Yes, of course. But then you have the lowest possible emissions. So if that performance matches.
Yeah.
Yeah, so
yes.
Okay, so that was the first part. So then that clarifies that use of the term optimal. Maybe to me, I think that would have been good if paper 4 clarifies that more. That is because it's a very specific type of optimization, which you in general don't talk about in relation to cell design.
Yes.
And my second, I have couple of questions, and they relate to the integrated assessment model, which you already talked about. And I think that Dr. Baumann did a good job on this, but there are a few things which I wonder about here. And it is, in the case here, you during the discussion clarified then that when you take the scenario coming from this model and you use the Python method in the Python package in premise to modify the EchoInvent database, which you use for the unit process data sets. And here I wonder, the first question I have, did you operate that on system data sets, or do you modify singular unit process data sets throughout the entire database? How does the premise package work in that case?
The premise is so for the integrated assessment model, and for example, for a certain material efficiency or something, there is a ratio, and how much efficient it will be, the process it will be in the future in different years, and such it's like implemented in the corresponding processes in the LCA database.
So it goes to the specific unit process to modify that, right?
Yeah.
Yeah. And so it modifies the energy input, and it modifies also the material efficiency, if I get it. Does the tool modify specific emissions? So is there a technology improvement emission correction? Let's say if nuclear power is improved for ionizing emissions, does that also change that? So it actually changes the elementary flows out of each unit process.
Yes, the elementary flow also changes when it comes to like the efficiency.
But only related to climate. I wonder this because this is a key thing for one of the arguments you use later on for why you're only looking at climate impacts.
The reason why I only use climate impact also because, for example, remind integrated assessment model, it focuses on very specific sectors that is more related to climate impact, like the energy sector related. For the chemical industry and other, it's not really considered.
No.
So the uncertainty between the impacted categories will be higher if we. I mean, of course, we can consider, but then the trade-offs, then it could be tricky to discuss.
Because I don't really see that point, to be honest. If the material efficiency is increased in each of the processes and the energy is changed, it could be equally valid to evaluate any impact category. It's just that it's done under the circumstance that the scenario is meeting a specific goal, and that is a climate goal. So it's not addressing, let's say, a resource goal or an acidification goal or a eutrophication goal, but it's addressing climate, but you could still assess the other impact categories, to me, unless specifically only certain elementary flows of greenhouse gases are changed, whereas others are not, because then you could get, but still in that case, where the data sets are not fully internally balanced. But then on the other hand, that's a weakness of the change process, which should be further highlighted, I think. And I don't really know the details of this, so I'm genuinely curious. Not only what your knowledge about it is, I'm really wondering how this works, and it really determines how you should choose your impact assessment methods connected to this kind of model use. Do you have any additional reflections on that? It's a tricky question. I fully admit that.
Yeah, I don't, but it is also discussed in other papers related to prospective LCA, that the reason why normally when using premise, when the prospective LCA using premise, with they only consider climate impacts. This is because of the limitation of the integrated assessment model, more focusing on the climate impacts sector.
Yeah. All right. Yep. So two shorter follow-ups on that, because you then draw. I mean, you have certain sectors which are addressed here. So the steel is changed, and definitely energy. So the electricity mix is changed, and so on. So we're shifting down, decarbonizing certain sectors, and some sectors, for example, chemicals, are not. And then, knowing this, we can see that okay. So the sodium-ion batteries and also the solid-state batteries, they are actually in your model not reaching below the potential of what you now model for lithium-ion batteries. So do you see that there is a risk here of these novel technologies, which are in some cases reliant on other sets of chemistries and maybe more dependent on the performance of the chemical industry, that you underestimate the reduction potential of, for example, sodium-ion batteries? Or do you see that there is a risk of a gap here, or do you see that it's well covered? Do you have justification for the final conclusion that you draw, that you don't really see sodium-ion batteries go below than lithium-ion batteries?
I think the reason why sodium-ion batteries is not go below is related to the low specific energy. It's related to the functional unit that we choose here. It's not because the emission it's specifically higher per unit of material.
Okay, so then it is relatively robust. So that's a good. Okay, that's good. So and then the final question is that so now then you know this. What is your general reflection on these emerging technologies? Should we pursue sodium-ion batteries not only for economical reasons but for sustainability reasons? Given that you actually do conclude that maybe the most promising solution is the lithium-ion battery technology.
No, actually, I think economic reason is very important because, I mean, we also we talk about electrifying everything, but lithium-ion battery it's still quite costly, and it's not so fair for a lot of emerging economies and also like developing countries. It's very hard for them to electrify the vehicle market. Sodium-ion battery is just provide like a better solution if the economic cost can really achieve like 30% lower than lithium-ion battery. It depends on what we substitute. Yes, now according to the results, sodium-ion battery could be comparable or higher climate impacts than lithium-ion battery. But if we compare substituting like the internal combustion engine vehicles, it's still like worth to promote such technology. Also, like sodium-ion batteries, working wise, it works much better under cold temperature. So it's in many cold regions, like here might be.
Yeah, there are many good reasons. I fully agree. So I stop there. Thank you. Thanks a lot.
Thank you very much.
Thank you, Anders. And also, we just want to welcome now Jennifer Dunn from Northwestern University. It looks like you have a cold or something, but I'm sorry. I hope you're okay anyway. So maybe we can continue with you, Jennifer. And
yeah, sounds good. Yes, I'm not crying. So, anyway. So yes, it's really nice to meet you, and it's been great to hear about your work and to read your thesis, and to make this connection with your institution. So thank you for the opportunity to be here. I have questions that kind of center on the use of lab scale data, but I am a chemical engineer, and so in my work in my group, we do a lot of prospective LCA of emerging processes for lots of different applications. But I'm curious about your thoughts on, risks, and some of these you expounded on in your writing, but risks associated with using laboratory scale data as the foundation for life cycle assessment. What are some risks you see with that?
First, it's like the synthesis method or synthesis route that we use at laboratory scale might not be representative. Like after upscaling, like probably we might use totally different synthesis method, and some input material might also be changed. But this is like the risk, but such risk is quite hard to take into consideration. But it's important to be aware of that when interpreting the results.
Though I've had people tell me, like, why do you bother doing this? Why do you bother doing prospective LCA with laboratory scale data when there are so many things that can change? Like, what's the value in doing that type of analysis at that stage, at that technology readiness level? What would you say to people with those types of comments?
I think it really depends on the technology, if it's really promising or not. So if it's really promising, even though it's at like small scale or low TRL, I think it's still worth to try to have a snapshot of of how it might look like in the future. Might not be representative, but just to have like a very quick calculation by the empirical factors or the general processing engineering equations to see how the environmental hotspots might change. And that might give like some indicate how to improve the process further for the chemical engineering who's developing the chemical reactions, and also for the people who will be use the laboratory synthesis method to upscale it to industrial scale.
So I could be wrong, but in paper 1,
yeah,
I didn't see a comparison to like an existing commercial scale product. Did you compare to an existing commercial scale product?
In paper 1, it focused on it's the organic battery and focused on laboratory scale.
Right.
Use the laboratory scale LC, but on paper 2, we upscaled the laboratory scale, use like the empirical factor and processing equations to the industry scale, and compared not to the commercial lithium-ion battery, but also to the emerging flexible lithium-ion battery at the similar TRL. Similar TRL only at technology level, but not at battery component level. So honestly, it's not really a good comparison, which also needs to be taken into consideration, but it's also discussed in the paper.
So another, kind of point of discussion I'm often engaged in with people is if you're going to do a prospective LCA of an emerging technology, what are your thoughts on the need to be able to compare an emerging technology to an existing technology in a way that lets you determine or like have some insight into whether there's any hope that that emerging technology will have competitive environmental advantages with this commercial scale technology, right? So the two papers there, I don't think that you're able to comment on like okay, these technologies compared to what we have today that we're using all over the place, that these offer an advantage. Would you push
Yeah.
back?
Oh, sorry. Say,
Oh,
could you say it again?
Would you push back on that? Would you push back on that type of assertion about your work?
I think it's still valid for, because it's provide like a new application or user experience. So it's very hard to compare it with, there's no exist technology. That's why that product was not compared to existing technology.
And then I have
It
one
was
more.
more like focusing on the, actually, it was more like focusing on the product itself rather than make a comparison to see, okay, if it's better or not.
I see. Okay, and then I
Yes.
can ask another question about cost, right? And so, where do you think the relative considerations of cost versus environmental effect should come into play? Because this analysis focuses primarily on the environmental performance, but at some point, like a decision in how the process will be scaled up will be based on relative costs of various inputs and whatnot that might not be apparent at the lab scale. Like I don't do lab research anymore, but when I used to in grad school, I didn't even think about the cost of solvents, or I just like whatever we had in the lab that was going to work, I just used it. So if you're taking data from lab people, maybe they're not thinking about cost. And so I'm just curious your thoughts on how you kind of might, in a prospective LCA, take into account some factor of cost and how decisions might be influenced by the cost of various inputs that aren't being considered at these early stages.
I think it could be interesting to think about cost if there's like multiple possible production processes of the emerging technology or emerging chemicals, to see like the environmental perspective and the cost perspective for comparison.
Okay, and I'll just ask one more question. So the role of uncertainty in these types of analyses, right? So I think you've done some different scenarios, but I'm curious if you had more time for your work, what you might do, how you might extend your work to characterize uncertainty.
I think I would like to do a global sensitivity analysis, especially for the battery design model, and to see, because there are different parameters were changed in the baseline scenario and optimal scenario, just to say, okay, exactly which one, what is the relative contribution of each of the parameters to the final uncertainties, and which also represent like if the uncertainty is high, also indicates there's more room to be optimized for that specific parameter.
When you're interacting with laboratory scientists, do they ever provide uncertainty around their values? So like a standard deviation or anything like that, if they're giving you a solvent consumption rate or other factors from their laboratory, are you ever able to work with them to characterize the uncertainty in their laboratory parameters?
Actually, no. From my communication to based on my communication or based on my feeling, during we communicate, actually they don't really care about how much solvent or how much solvents that they use, because their aim is to get the wanted chemicals, not for improving yields or improving the production, the material use efficiency. So
Maybe I should change my
Yeah.
example. Let's say in yield. Do they ever communicate an uncertainty to you in their value for yield?
No, actually, no.
Okay.
Also because like the specific people that I talk in the lab, they as we see just now, it was more for the conducting redox polymer, not for like it's like very fine chemicals. So it's more like their aim is to get the chemical that they want rather than getting like a chemical with a high yield.
Okay. Okay. I'll conclude my questions. I don't want to take up too much time.
Thank you
you.
very much.
Thank you. Okay, and then we move to Christoph.
Thank you very much. Yes, thank you, Shan, also for the very nice presentation. And I know this is quite a marathon to answer all the questions, so stay with us for a little bit. You're getting there. So I have a few questions, and the first one is maybe a two-part question, but I will focus on the first one in regards to the beginning of your conclusion. And in the beginning of the conclusion, you ask, or you write that you find that the various technologies that you looked at either have a higher environmental impact or has a higher climate impact, or that they are comparable. And these are like still like rather strong statements saying that they have a higher environmental footprint. And I would like to ask, like, what does it take for you to really define that come to the conclusion that it definitely has a higher environmental or climate footprint? Where are like thresholds for getting to different levels of commitment, so to speak, in your conclusion?
Yeah, actually, it's also like, thanks for the question. I should have said it in a different way, have the potential or something. Because it also depends on the functional units that we consider here. The functional unit is only focusing on battery store capacity. If, as me and my opponent discussed just now, when other factors or parameters gets into consideration, like life cycle and energy efficiency, then it might totally change the picture, because some battery could have higher or potential have higher climate impact in the battery production process, but then they have really long life. And if we consider this in the functional unit, then that might really change the conclusion. So yeah, I think the conclusion that I gave should be more clear. It was based on the functional unit of per kilowatt hour of battery storage.
Which you do mention, yes. So that's definitely mentioned in the text. So a second question on the same paragraph, more or less, and that links a little bit to Anders' last question, is now imagine you are one specific stakeholder, say, for example, a government handing out either subsidies or funding money for further research, and you read such a passage. If you're now talking to such a stakeholder, or you're that stakeholder yourself, does that would you draw the conclusion that potentially we should just stick with LIB batteries and not go for post-lithium if they don't provide a specific benefit for in terms of the carbon impacts?
I was more thinking because, and the reason why all this emerging technology exists is because of their benefit in other perspective, like the cost or higher specific energy. So I feel like we cannot stop like the involvement of the technology development. It will be on the market. It's quite clear a lot of investment and money is in this. But what we could do as a LSA practitioner is like we could provide like okay, if we want to improve the climate impacts or the environmental impacts, on what part can we focus on? That is the message I think is better to deliver. Because as I feel like, for example, also solid state battery, even though they have higher climate impact, but then they facilitate the electrification of the vehicle in some sector that the customer wants longer driving range, because there's also like a driving range anxiety. So this part, it's also like like how do we look at the picture? Like what does the battery substitute? Does it substitute lithium-ion battery, or does it substitute internal combustion engine? If it substitute internal combustion engine, then it's good. If it substitute lithium-ion, probably it's not good, but then the whole society want to electrify it, the vehicle sector.
Right. Thanks a lot. I want to go a little bit more into how you collected your data and also how you would advise other people to collect their data. So you mentioned that you got some lab scale data also from colleagues from Uppsala. You got a lot of information also from going through the literature and using life cycle inventories from others to compare that. So when you see a life cycle inventory from a different group that's published somewhere, what kind of like quality criteria do you go through? What kind of what is your like checklist of things that you look at to see whether you would like to use that inventory data or disregard it because it's not fitting maybe? So what are selection criteria for a good lifecycle inventory?
First, I would say how they get their data. So if it's like directly from industry, of course, then it's good. Also, what is the assumption behind of the data? And how detailed the data is provided, because some data probably they are good, but then they are very aggregated. It's quite hard to use if we want to really identify the environmental specific unit process in the environmental hotspots that caused by specific unit processes. So, and also the time perspective as well.
So you mean
yeah.
the older the data is, the less relevant, you mean? Or
I would say so.
Mhm.
It depends on different sectors as well, because for some sector, the data probably will not change that much over time. But for some sector that is developing really fast, then the more updated data set is better.
Did you run, I mean, you already said that you modified some of your data set based on these premise integrated assessment modeling, but did you also run into aspects of different geographical scope than, so for example, if life cycle inventory was specific for Australia only, maybe? So what are things that you could do then if you have like a little bit of a missing geographical scope?
You mean life cycle inventory specifically for
Yeah.
one? Yeah. It depends on how the unit process would change related to the location, because a lot of unit process, like for production, it's less relevant to where it is located. For example, the energy, how much energy is used for producing certain things. probably the climate impacts will be different because the emission factor of the electricity or energy is different in different places. But then the amount of energy that is used is less relevant.
Mhm.
So I would use such, yeah.
Right. Thanks. So when we talk a little bit, a lot with like engineering or chemistry colleagues, when we talk about uncertainty again, their understanding of uncertainty is a drastically different one. And if we then tell them, yeah, well, it maybe have like plus or minus 10 or 20%, I don't know exactly the final result, they will have very large eyes and be a little bit surprised because they have used to much more certain experimental data very often, of course. What is an uncertainty range that LCA practitioners should aim for? And is it, or what are criteria when people, researchers from our field, should be like confident about their results or happy that they got their uncertainty range to sufficiently low number? Can you give some indication there or some criteria how people can obtain such a conclusion?
In general, I feel like all LCA has uncertainties, and it's not for me. Looking at LCA is not for the specific number, but rather than like the general trend. Whereas the environmental hotspots, or in general, like how one product gets better or worse compared to the other. When it comes to uncertainty, I was more thinking if in the upscaling, one big uncertainty is what we don't know is that how big the industry scale would be. And different industrial scale, the related parameter for different industry scale really affect the final results quite a lot. And that information needs to be clearly communicated. When you upscale, okay, then is it like gigafactory or what factory? Sorry, probably I didn't really answer your question. Could you?
I mean, you have shown your uncertainties mostly with some scenarios that you have. You did not give like say Monte Carlo simulation or whatever, and giving it like a range for exactly every data point that you had. Some people decide to do such analysis. You also briefly mentioned in the discussion now that you would like to do a global sensitivity analysis for the most important range or uncertainty. But my question is more like on at which point are we happy with the results, and where do we stop improving our data because we got to a point where we're fine as researchers. So also for you, like where did you stop trying to improve your data, except for time reasons, maybe?
I feel like for emerging technologies, probably it doesn't directly answer your question because I feel like the larger uncertainty, it also indicates like a larger chance to improve. Because it's when we look at future technology, it's not really on the market yet, which means there are many parameters or things that we could play with. If there's like larger uncertainty on certain parameter or certain things, it means that there's like a bigger that could be indicate like there's a bigger opportunity that we could improve in this certain parameter, since there are like a big range in it. So I might see uncertainty in another way, because I see it also like an opportunity to improve for the future.
All right, thanks.
Also, like when we talk about Monte Carlo simulation or global sensitivity, sorry to interrupt, sensitivity analysis, we also need to know like how the distribution of the thing, and for each, it's really hard to get such data or information they at early development stage, as we said, the people from the laboratory or they don't have this the same thoughts as we are thinking. So I think that's also like a challenging part.
Yeah.
And regarding uncertainty, for example, if we talk about the prospective LSA, which use integrated assessment model, the different scenarios that we take into account also indicates the uncertainty, because in the future nobody knows like how the society would go. So we have different scenarios taking into account just to see like the what could be the range and how much it varies.
All right, thanks. So I want to go into one last block. Maybe it's just one question. Maybe depending on the answer, there might be a follow-up question. And the last theme, so to speak, is the system boundary and the omission of the end of life phase. So when we compare, for example, the life cycle stages that need to be included in the carbon footprint according to the battery regulation in the European Union. For example, there we have from extraction to end of life, excluding the use phase. So end of life phase and recycling and deposit of batteries is definitely included. You excluded it. You briefly mentioned that some recycled content could be included in some of the inventories, but mostly you excluded it. So how important is that that we exclude or include this end of life phase? What kind of errors could occur? How important is that also in the comparison of the final numbers when we talk about LIBs, lithium batteries, where normally in the carbon footprint according to the battery regulation, the end of life would be included. So maybe you can elaborate once again a little bit on why you chose this system boundary and what would have been necessary really to fully include an end of life stage in your assessment.
First is because, for example, for like the third and fourth study, sodium-ion batteries and all solid-state batteries, we looked into the climate impact of the battery production over different years. And the end of life comes, for example, if we produce the battery at year 2025, the end of life could come to 2035. And normally for normal for a lot of LSA studies, they wouldn't take this time perspective into account. But since we take the time perspective into the account, then how do we, because it's a bit tricky methodology wise, like how do we actually account like what the end of life? That's one of the thing that I was thinking. And the second is that there are different recycling methods, which is like not so sure like which one would be like more promising or something, like the direct recycle or hydrometal or pyrometallurgical or hydrometallurgical. Yeah.
Without having done the calculations, maybe, but do you have like an indication, like an order of magnitude by how much the carbon footprint of a lithium-ion battery would be reduced if you would include recycling into the system boundary?
Actually, the the climate impacts will only increase rather than reduce if we include the end of life, because we already include the recycling content. We already account the benefit, but we didn't really account the cost.
Right. With that specific
Yes.
allocation regarding the life
Yeah,
cycle,
because
stages.
we
All right.
use like a cut-off method for the
Mm.
whole, for all the studies.
Okay. All right. Thanks. Then I will leave it at that. Thanks a lot.
Thank you very much.
Thank you. And now we will also give the reserve member Annika a chance to ask some questions.
Okay. Thank you, Shan, for a nice presentation and a nice discussion. To me, this prospective LCA was the first time I heard about it. So you make assumptions for the future, but so my question is like how do you like validate? Like, is it a continuous work on like going back to previous prospective LCAs to see like how well this assumption held, and is this an like iterative work to refine the assumptions made?
Yeah, actually, I think for integrated assessment model, they do update because we use their results to integrate it in LCA. They do update every now and then. So the results could change if we use different versions of implementing different versions of model in the LCA. Yes.
So like in 50 years, then you can go back and check your assumptions and see like if there are new projections about the future. In paper 3, the future climate impact of sodium-ion batteries, you choose the sodium-ion batteries based on the TRL level to be rather high, even though it was a prospective LCA that accounted for like improvements in the battery performance. Is it possible that there is like other sodium-ion batteries that is at a lower TRL but could be better from a sustainability point of view?
How did we choose the battery chemistry was based on the market choice, because there are different, at that point when we were conducting the study, I read around and there are different like starting up companies focusing on different battery chemistries. And in general, of course, there are like 3 main types: layered oxide, polyanion, and pressure blue analog. And that was the specific chemistry was selected based on how the startup company focused on. So I guess they already had a different like experiment to experience different chemistries, and since they selected it for continuing like upscaling it, so I guess that was like a promising one. That was how it was selected. But that could be like some other sodium ion battery chemistries that would be performed better in the future if they discover any. But I'm not so aware of that.
And a very general concluding questions, like now you're at another state than what you were like 4 years ago. Like if you reconsidered like your thesis project, what would you, is there some certain things that you would have done differently?
Yeah, I think the thesis in general is quite flat. It's like using LCA on 3 different batteries. Then if I could reconsider, then I would add more element, probably focusing on 2 main part like sodium ion and also all solid states, which focus on like main more general applications or large scale applications. And then also consider their economic perspective and also some social perspective. That's something that I would like to do.
Thank you.
Yeah, thank you very much.
Great, thanks everyone in the committee and also the opponents. So now the floor is open for the audience. Any questions? No questions from online, or is this online also? No. No questions. Yeah, I had questions, but they were asked by the committee. So I don't know. Good work, I guess. But so actually, I don't have any questions either. So with that, I would like to thank you, Shan, for a very good presentation and also discussion here. Thank the opponent and also thank the committee. So let's just give them all applause.